Okay, well, we've looked at very simple heap files, well, depending on what order you looked at these videos in, but now let's look at sorted files. So basically a sorted file is one where the file is stored in order based on some key value, based on the value of an attribute, which we'll call a key. So these things you can imagine are tuples, and the values are the keys in those tuples. So you can see that they're stored in order. We assume that we can fit 4 tuples per page. If we have a very naive approach to insertion, we want to insert the tuple G. It has to go in this page in between F and H, but this page is already full. Therefore, we would have to move I into a page which is already full. Therefore, we would need to move the largest value in that page to a new page. So it could result in a substantial rearrangement of data in the file. So to handle that, we can introduce overflow pages. So if we do try to insert in a full page, rather than pushing these along, we simply add a new page here and put the new tuple in there. And if this fills up, then we add another overflow page attached to that and put more tuples in there. So this file structure is actually quite common. The overflow file, which I've represented as chains here, is actually a file, of course, and these pages could appear in any order in the overflow file. But the size of the overflow file will denote by BOV, and the average overflow chain length is just BOV divided by the total number of data pages. And we can view a data page plus its associated overflow pages as a bucket. Alright, so if we're trying to do selection on a file having this structure, then we can use binary search, okay? You've got a sorted array, you want to check whether an element's in the array, you can use binary search. Here, things are a little bit different because we're talking about pages, and in fact, more than pages, we're talking about buckets. Alright, so the standard binary search is you set the low and high values initially to the bottom of the array, the bottom of the data file in this case, and you set the high value to the last index, the last page index in the file. And you keep scanning until low goes beyond high, in which case you know that the value you're looking for isn't in the file. Alright, so binary search, you find the midpoint, the middle page, and you search that page plus its associated overflow pages, and they return you a number of things. They return a tuple, possibly. If the tuple you're looking for, the tuple with attribute k equal to value, isn't in this page, then this will be set to null. The other things that we return from a search of the bucket is what's the lowest key value in the bucket and what's the highest key value. So minimum and maximum key values. So the search bucket function takes the relation, the page ID of the middle page, the name of the attribute if you like, and the value that we're looking for that attribute. Alright, if we return a null tuple, if the tuple value that we returned is not null, it basically means we found the tuple somewhere in this bucket and we return the result of that tuple. Now here we're assuming that we're dealing with queries that have a single result. Alright, if the tuple value is null, it means we didn't find the relevant tuple in that bucket, so then we need to check which part of the file we need to consider now. So if the value that we're searching for is lower than the lowest value in the bucket, then we go to the left towards the bottom of the file. If the value is greater than the highest value in the bucket, then we go to the right. So we look at the top part of the file. And otherwise, if the tuple's not null and the value is not less than the low value, not greater than the high value, then clearly there is no tuple with this particular value. Also, if we reach a point where low becomes greater than high, we know that the tuple, there is no such tuple in the table. Okay, so basically it's a standard binary search algorithm, just expressed in terms of page indexes rather than array indexes. Right, what about this search bucket thing? Alright, so we're searching in a bucket whose primary data page is P, so we get that page, put it in a buffer, and then we search through the buffer looking for this K attribute having this particular value, and we initialize the min value and max value to plus infinity and minus infinity, so that we're guaranteed, assuming there are any tuples in the page, which I guess we could have checked, that we're going to set values for the min and max. Alright, if we find the tuple, once again, then we return the tuple and the min and max values. Otherwise, we start looking in the overflow chain. And so we need to open the overflow file and fetch a page from the overflow file, or at least find the page ID within the overflow file of the overflow page associated with this page. Alright, and then we scan along the overflow chain. So there are two ways we can stop scanning the overflow chain, is if we find the tuple that we're looking for, or if we reach the end of the overflow chain. So an overflow chain, each page in an overflow chain will have an index of the next page in the overflow chain, or it will have an index no page, meaning that's the end of the overflow chain. Alright, so we get the next page from the overflow file and store it in the buffer, and then we search this buffer. Now notice that now we're using min and max because those values were set when we looked at the primary data page. And so we need to pass these values in, so if we find a smaller value in the overflow page, that becomes the new min. If we find a value larger than max in the overflow page, that becomes the new max. And of course we chain from overflow page to overflow page by looking for the overflow index in the buffer. And so ultimately we return whether we found the tuple. It may still be null, or it may be, or maybe we did find a tuple somewhere in the overflow chain, and we return the minimum and maximum values that we found in the overflow chain. Alright, so searching the bucket required a search page function. So we got a buffer full of tuples, we got a field or an attribute that we're interested in, we've got a value that we're looking for that attribute, and we've got the current min and max values. Alright, so initially the result is null. We assume we're not going to find a tuple in the page, and then we iterate through all of the tuples in the page, look at each tuple. If the value that we're searching for happens to be in the tuple that we just got, then we're done. So that's our result. If the k value in the tuple happens to be less than the minimum value we've seen so far, well, that becomes the new minimum value. And similarly, if the k attribute has a value that's larger than the maximum value that we've seen so far, then that becomes the new max. And ultimately we return this triple. Now, of course, this isn't C because you can't return a triple of values, or at least you couldn't in the older versions of C that I have dealt with. Alright, so essentially the technique that we just talked about uses each bucket treats it as if it's a single large page, and we're finding the minimum value and the maximum value stored on that page, and if the tuple's there, then we'll find that as well. So what about the cost for doing this kind of selection? Well, the best case is that the mid page happens to contain the tuple we're looking for. So the first bucket search on the mid page finds the tuple and we're done. In the worst case, we have to do a complete binary search, which basically means we need to examine log2b data pages, plus we need to look at all of the associated overflow pages for these particular data pages. So the worst case scenario is that we do log2b, is that we look at log2b pages in the data file, plus we look at their associated overflow pages. And in this case, the real worst case scenario is that all of the overflow pages are associated with the pages that we happen to look at. Average case, we examine some data pages. We don't go all the way to log2b data pages, but we look at some and we look at their overflow pages. So the things you can characterize the most easily, in the best case we read a single page, in the worst case we read log2b data pages plus all of the overflow pages. And as it says here, if you want to try and do an average case cost analysis, you need to know something about how the data is distributed and so on. So are there lots of small values in the data file, in which case the average cost is going to be skewed towards the lower end of the data file. Alright, so all of that was dealing with a one query, so we know there was a single match. For a partial match retrieval query on an attribute that's not unique, so we can have a number of tuples with the same k value. So here we're looking for a k value of 2. Our binary search, well, the first data page where we have a match is the mid page. That's the first page that we're going to find when we start doing our binary search. But we're not done, because there may be more tuples that have a value of k equals 2. Now they could be further up or they could be further back, so we actually have to look in both directions. Here we wouldn't have to look much further, because we'd see that the maximum value in this page is greater than 2. So we know that if there are any 2 values in this page, or rather, putting it another way, there are guaranteed to be no 2 values further up the file. However, if we go back to the previous page, that's all 2s, and if we go back to the page before that, we can find a number of 2s, but the minimum value is less than 2, so we know there's no point going any further, not to mention the fact that it's the first page in the data file anyway. So this process starts with a standard binary search of the kind that we just looked at before. Once we've done that binary search, then we have to scan backwards and forwards a number of pages to find all of the matching tuples. How many pages do you have to scan backwards and forwards? Well, I've already talked about the quantity BQ as being the number of pages that contain matching tuples. And for each page that contains matching tuples, it may have associated overflow pages, so we take account of that cost. And you notice there's -1 here. Why do we do 1 less than the number of pages that contains matching tuples? Well, because the initial page containing a matching tuple was actually found in this step, so we've already accounted for reading that. But then we have to read all the other pages, or all the other buckets, if you like, that contain matching tuples. If we didn't have any overflows, then we just throw that term out. We'd simply BQ -1. Right, if we've got range queries on a unique key, so let's say we're looking for all k values in the range 5 to 13, we could start by finding the lower bound. So we could search for k equals 5, and the binary search in this case ends up here. So we need to scan. So this is a unique key, so we know there's no other 5s in the file. And 5 is the minimum value in this page, which we could easily work out. Therefore, we don't need to scan further back, but we do need to scan forward while we find values that fall within the range. And we scan forward until we find a k value that's larger than 13. So when we reach this page, we look at that tuple, then we look at this tuple and say, well, that's larger than the upper bound of our scan, so we'd stop at that point. So the cost is similar to the partial match retrieval one that we saw on the previous page. How many pages are involved? Well, the number of pages that contain matching tuples. We subtract 1 because the initial page containing the first matching tuple was accounted for here. And if you think about it, we're going to be, and we've got buffering. Here we're assuming that we don't have any buffering, but the fact that we've done a binary search and we've already looked at this page when we were searching for k equals 5, then this might well be buffered already. So, in fact, we wouldn't have to read a total of BQ pages while we're scanning, because some of them might already be in the buffer pool. Right, but once again, we're assuming that we don't have a buffer pool, so that's the total number of page reads. If we're doing range queries on a non-unique key, then we have a similar kind of approach to what we did with partial match retrieval. Once again, the binary search is going to find a match. So we're looking for the lower bound. We find a tuple with the lower bound in this page, which is the first page we look at. But then we have to go further back to see how many other tuples there are with k equals 2. Once we've exhausted that, we go forward looking for a tuple that's larger than that upper bound. And so we'd go through here, and when we eventually found this tuple, we'd stop our scan because we would have found all of the tuples that satisfy that condition. So once again, cost analysis is the same as before. We've got the cost of doing a binary search to find the initial tuple, and then how many other pages do we have to read backwards and forwards to capture all of the pages that contain matching tuples, which is BQ. And if we're dealing with overflow pages, we have to read them as well. All right, so all of our all of our where clause conditions so far assume that the query was based on the sort key. What happens if we ask a query that doesn't involve the sort key? So there's no mention of K here. I guess it's remotely possible that the file is sorted by J, but as well as K, but that's extremely unlikely that we'd be sorted on both of them. So remember that we said the sort key was K, so the file is sorted by K. So in fact, the fact that it's sorted on K doesn't help you at all finding particular values of J. They could be anywhere in the file. So we have to scan the entire file, regardless of the type of query that we're dealing with. If we're doing insertion, I alluded to the fact that we'd need to create overflow pages, possibly, once we try to insert into a full page. So we can have a look at this example down here. So if we try to insert k equals 33, well, there's space in this page where a previous tuple has been deleted. If we're talking MVCC, then there's also an empty slot here that we could put k equals 33 into. Now within a page, the tuples don't necessarily have to be sorted by the key, although it might be convenient to do that. If we then try to insert k equals 25, then the minimum value here is k equals 30, so k equals 25 doesn't belong in this page, and k equals 25 is obviously greater than the largest value here, k equals 7, so k equals 25 belongs in this page, but this page is full. Once again, if we're talking MVCC, we have to leave that deleted tuple. So we'd say, all right, this page is full. Let's have a look at its overflow. The overflow page is full. So we come to the next overflow page and we insert 25 in there. If there was no overflow page beyond this, then we have to make a new one, link it together, and then put k equals 25 in there. Alright, what if we try to insert k equals 99? Alright, well that's going to end up in page 4, which we'll discover by doing our binary search and discover that the value that we're trying to insert is larger than any of the values in here. So in that case, we'd have to create a new overflow page, link it to this page, and then store k equals 99 there. Once again, that's assuming that this deleted tuple has to hang around until the next vacuum. So if we're talking Postgres, for example. Deletion from sorted tuples is basically we're doing a search because we've got a where clause. So we're searching for matching tuples. When we find them, we mark them as deleted, and we have to write out the page containing the deleted tuples. Or at the very least, we mark it as being dirty and release it. How much it's going to cost, and pretty much this actually applied to the earlier selection examples as well. It depends how frequently this value appears in the file. If it's a primary key, okay, it's only going to appear once, but if it's not a primary key, there may be multiple pages that contain matching tuples, so we're going to have to delete them all. So we have to find the start page, and then we have to write out, which is what the W subscript is, all of the pages that contain matching tuples. So there are BQ of them. So there are BQ writes. So this is the cost for doing the selection. Basically, this finds all of the pages containing matching tuples, and this is the cost of writing them out. Okay, so that's all of the operations on sorted files. I've been a little bit terse on the insertion and deletion, but hopefully you could flesh out the algorithms for doing that. Okay.